All right, so the final video to review fundamentals is going to be about mole conversions and stoichiometry, relating the different quantities that are equivalent to a mole to one another, and being able to use those quantities to relate reactants and products in a chemical equation to one another. You may remember from your previous chemistry studies that 1 mole of any substance is equivalent to its molar mass in grams, which we can get from the periodic table using its chemical formula. That the mole is defined as the number of particles that are present in that substance, which is going to be 6.02 times 10 to the 23rd. Those particles can be represented as atoms or ions or molecules or formula units. And then all of those are the equivalent for gases at STP to 22.4 liters, STP representing standard temperature and pressure, 0 degrees Celsius and 1 atmosphere. When you're looking at the percentage of an element or an ion making up a compound, you can determine that by taking the grams of what you're looking at and dividing it by the grams of the whole compound and then multiplying it by 100. Stoichiometry is going to follow a lot along with mole bridges, only you need to account for the stoichiometric ratio between the two substances you're comparing, and you're going to get that from the coefficients and the balanced equation. Both the mole bridge and stoichiometry are going to involve functional analysis, which we covered, I believe, in your second video. So our first example, how many liters are in 24 grams of CO2 at STP? Anytime you have grams, you're going to need to use your periodic table to calculate your molar mass. So I would encourage you to have your periodic table out when you're working mole conversions, stoichiometry problems. We start these problems just like we did with dimensional analysis with what we were given, the 24 grams of CO2. We're going to set up our units to cancel out the grams and to find liters. Remember we said that a mole of a substance is equal to its molar mass in grams. So if we go find carbon and oxygen on our periodic table, we have 1 carbon in this formula and 2 oxygens. The mass of carbon is 12.01, the mass of oxygen is 16. We need to double oxygen's mass because there's 2 oxygens in CO2, and we add it to carbon to get 44.01. And just like in your first year class, we're going to round our masses to 2 decimal places. So that's going to be what is equivalent to 1 mole of CO2. And remember we said that 1 mole at STP is going to be equal for gases to 22.4 liters. And carbon dioxide is what you exhale every time you breathe. So that is definitely a gas at standard temperature. And so 22.4 liters is going to be put in the numerator. Our grams cancel out. We need to multiply our numerators together, and we need to multiply our denominators together. In terms of sig figs, you are going to want to look at sig figs for your molar mass and your molar volume. The starting value had 2 sig figs, 2 non-zero digits. Your molar volume has 3 sig figs. Your molar mass has 4 sig figs. So the starting value is going to determine our sig figs in this problem. When I calculated this, I got 12.21540,559. I want 2 sig figs, so I'm going to keep the 1 and the 2, and then the second 2 that came after decimal will not round it up. So my final answer will be 12 liters. You can do mole conversion problems between grams and moles. You can do them between grams and particles. You can do them between moles and particles. You can do them between liters and particles. The units you use make no difference. You have to use those conversion factors that we talked about on the previous slide to relate whatever units you have to each other. In this example, we're going to calculate a percentage. We're going to calculate the percentage of magnesium nitrate of nitrogen, and then we're going to round our final answer to 0.1%. So to find the percentage of nitrogen in this compound, I need to know how much of the compound's mass is nitrogen and what is the overall mass of magnesium nitrate. I'm going back to my periodic table and finding the mass of Mg, N, and O. Mg I have 1 of, 24.31 grams. That 2 gets distributed through, so I have 2 nitrogens at 14.01 and 6 oxygens, 3 times 2, in the NO32 component. When I multiply through the amount of each element I have and then add their masses together, I get that the overall mass, the molar mass of magnesium nitrate is 148.33 grams. To find the percentage of just nitrogen, I'm going to take the part of the molar mass that was just nitrogen, the 2 times 14.01. I'm going to put that in the numerator. So I'm getting the component that I'm wanting to look at, 28.02 grams of nitrogen. I'm going to divide it by the mass of my whole compound, 148.33 grams. And then to turn it into a percentage, I multiply it by 100. When I divide these two by one another and then multiply by 100, I got 18.89031214. So I'm going to keep 18.8, and the 9 is going to make the 8 round up to 18.9%. You will notice that the grams cancel out, so the only unit that is associated with percent composition is that percentage sign. Our final example is going to be an example of stoichiometry. When you're dealing with stoichiometry, when you're switching between substances, you're going to be going from either a reactant to a product, or maybe a reactant to another reactant, a product to another product, or maybe a product back to a reactant. But you will only ever be dealing with two of the components in your chemical reaction at any given time. You have to have that balanced equation to be able to solve a stoichiometry problem, and you have to be able to identify what you're being given and of what substance and what you're trying to find out about your other substance. Here we want to know how many moles of silver sulfide, Ag2S, are produced from 3.01 times 10 to the 23rd molecules of molecular sulfur. I start with what I'm given, the 3.01 times 10 to the 23rd molecules of S8. Because that's what I'm starting with, that's what I want to cancel out, so it goes in my denominator. I'm trying to find out about moles of silver sulfide, so that's going to go in my numerator. We said back with our mole bridge that 1 mole of any substance is going to be equal to Avogadro's number of particles, which molecules is one of those, atoms, ions, molecules, formula units. Avogadro's number is going to go in front of molecules for S8, and because everything's defined in terms of 1 mole, 1's going to go in front of moles of Ag2S. I need to relate Ag2S to S8. All I've taken care of so far are the units, the moles, and the molecules. So I go up to my balanced equation and I look at the coefficients that are in front of S8. There's nothing there, so it's understood to be 1. And there's an 8 in front of Ag2S. So for every 1 mole of sulfur, I'm going to make 8 moles of silver sulfide. If I do not account for that ratio, I will not have the correct number of moles of silver sulfide. I have to account for the proportion, that's basically my recipe, that relates the two components to one another. At this point, I can see that I have units that cancel out. I should be able to multiply and divide. In terms of sig figs, I have 3 sig figs in my starting value. The coefficients do not have sig figs. Everything is defined in terms of 1 mole, so that 1 mole does not have sig figs, or is unlimited number of sig figs. And your Avogadro's number for our purposes had 3 sig figs. So since both the starting value and Avogadro's number had 3 sig figs, we're going to have 3 sig figs in our answer. I got exactly 4 on my calculator. So to show this as having 3 sig figs, I need to make sure I include the 2 zeros past the decimal, as those are trailing zeros, and with a decimal they will count as significant figures.